finally have enough to really use these Laplace transforms. Now the truth is, the full power of Laplace transforms won't come into being unless you go into structural engineering level 8, where for these kind of more complicated functions and dynamical loads and all these kind of things that comes in, or like a door closer with a kick, something like that, or a door closer with someone pushing between seconds 2 and 3. But this is we're looking at the basics. Like, you want to be quite good at what we're doing here before going to level 8. And as I said, like, you really don't want to be thinking in terms of doing the minimum on this. You want to do well, and you should be. We're going to be finished the lectures pretty early. You're going to be putting a lot of time into your exercises, because it is difficult. There's no two ways about it. But anyway, so this is something we've been talking about a few times. We'll see it again. So we're looking at a linear differential equation, which for us would be some constant times the second derivative plus some constant times the first derivative plus some constant times y of t is equal to something, which usually you'll be thinking of as an external force. So we have a method here, which I'm going to draw a picture of below, which we've seen a few times. But the 4 steps are, now the 4 steps, I mean, you say steps. I have a page somewhere. I might go and look for it. Yeah, so I have this page that kind of does go over all of the steps, but the point is, let me just show you. So these are all the steps. And the point is, there's too many steps to doing one of these questions. And it's like when you drive, say if you drive from one part of Cork City to the other, like say you're somewhere in Ballinlough and you're driving up to somewhere in Granabraher or something like that, you don't actually sit in the car and think to yourself, oh, what are the steps? That's not actually how you do it. You actually you sit in the car and you go, okay, I'm going towards Granabraher. Where do I go here? And I go, oh, I start by going right. And you get to the end of the road and there's a junction, and you make a decision at that point, where do I go next? Now you might have a rough idea overall, and that would be the 4 steps that I'm talking about on page 117. This is page 159, but you don't have every single step in your head before you start. It's more realistic that you just start driving, and each time you get to a junction, you think of, where do I go next? And this is the kind of understanding that we're going to go for. So those kind of methods of kind of learning the steps, you're reaching the end of that kind of, the maths is going to get beyond that. You won't be able to think like that. It's just too many steps. So, but the basic steps, like say if it's Ballinlough to Granabraher, might be, I don't know, get to South Terrace. That might be step 1. Get to, I don't know, get over to towards Blarney Street or something like that. Go up Blarney Street and then you're there, something like that. So these are the big 4 steps here. Take the Laplace transform both sides of the differential equation, apply the initial conditions, solve for the Laplace transform the solution, and then find the solution by applying the inverse transform. Now by far the inverse transform, step 4, is the hardest bit. Okay, but you'll want to do the first 3 steps. So we'll kind of draw a picture of this down below, one that we would have drawn earlier on. Just kind of jog your memory. So we're starting in what we call the time domain. So now it can actually be x as well, and usually it goes from 0 up. So it'll be t or x, and it's usually from 0 up to infinity. Okay. Now that's kind of complicating things, but I'm just saying, so it could be time, which can kind of go up to infinity, and x, which will be a distance along the beam. And what you have in here is a differential equation. Now the differential equation is this yoke up the top. Now what you want to do is you want to find the solution of that y of t, and it might be difficult to do that for various different reasons. So this is what you want to do. but this route is difficult. It turns out there's an alternative way of doing it where you translate it, the differential equation into it's called the S-domain. Now the S-domain are actually, although we don't see it, they're actually complex numbers. We don't really need to know that. And the thing that translates from the thing on the left to the thing on the right is this Laplace transform. So we translate the differential equation into an algebra equation, because what the Laplace transform does is it turns differentiation into multiplication. So now the thing is, an algebra equation, now this actually is supposed to be an L, but it's just not for, it looks a bit like an alpha. That's a bit better. Now it's very easy to solve an algebra equation. You've been doing that since you were young. But what you find is not y of t, but big Y of s. Okay, now there's something in here as well where you put in the initial conditions, but that's no issue. And then once you've solved the algebra equation, which is very easy, you do the inverse Laplace transform. Now you pay back the easiness, which is solving the algebra equation, by the inverse Laplace transform being difficult. But in the context that you really go into this in level 8, going the long way around with this Laplace transform and the inverse is a lot easier than any kind of direct methods along the dotted line. Now I have a little, if you like metaphors and stuff, I have a metaphor for this up here. So suppose that you come across a poem written in English. So that'll be the differential equation. And the English would be that it's in terms of time, whose meaning you don't understand. So the meaning would be the solution of the differential equation. And you don't understand it because you're not good at solving the differential equation. You're not good at finding out the meaning of the poem. However, suppose that you know a French-speaking gentleman named Pierre Simon. Now, that's Laplace's first name, who's a master of interpreting poems. Now, it's not actually that he's a master of interpreting poems, but in French, these poems are very, very easy to understand. The algebra equations are very easy to solve. So you get the poem translated into French and sent to Pierre Simon. Pierre Simon writes a perfectly good interpretation of the poem in French. So that's the big Y of S. And then he gets it translated back into English and sent to you. And that's how it works. So you want to kind of understand this big picture. And in terms of the steps, like I'm not really interested in steps, but first step is the Laplace transform. Second step is the initial conditions. Third step is solve the algebra equation. And the fourth step is sending back. Okay, and I think we'll do an example or two. Right, so we're keeping the 4 steps in our head, but we're not specifying this like this. The 4th step can be really, really long. Okay, so suppose the bending moment B of x at a beam. Now, I don't know why I use B rather than M here. There must have been some reason. Anyway, at a distance x along a beam satisfies this differential equation. Use only Laplace methods to solve this. So we take the Laplace transform of both sides. Now we're going to have to write some stuff from the tables. I'll write through them here. So one of them in the tables, it says that the second derivative gets sent by the Laplace transform to s squared times the Laplace transform of the function minus s times the value of the function at time domain at 0 minus the value of the derivative in the time domain at 0. If you want to see where all these formulas come from, there is some appendix, if you look through, which has this. And a constant is sent to constant over s. Okay, now one of the things here is, let's see our notation. So we've got b of x. Now it's always going to go to s. So we're going to send this to, now we'll do little b to big B of s. Okay, so off we go. So take the Laplace transform of both sides. So the second derivative, now I have to use the first orange formula up the top. So the s squared bit is okay. Now the big F of s, now remember this second derivative here is b double dashed of x. And so if we're sending f double dashed of x, we get this big F, but we're sending b double dashed of x, so it'll be big B. okay, minus s times, now we're sending b double dash, so it won't be little f of 0, it'll be little b of 0. And then minus, it won't be little f dashed of 0, it'll be little b dashed of 0. Equal to, what's minus 12 sent to, using the thing in the top right hand corner, minus 12 over s. So that's step 1. Step 2 is apply the initial conditions. B of 0 is 0, b dashed of 0 is 36. So we get s squared times big B of s minus s times b of 0, s times 0 is 0, minus 36 is b dashed of 0 equal to minus 12 divided by s. Now our job is to solve, that's the first 2 steps. Now our job is to solve for big B of s. So we're going to add the 36 to both sides. So we get 36 minus 12 over s. And now we're going to divide both sides by s squared. It'll get rid of the s squared on the left. 36 divided by s squared is 36 divided by s squared. And then we have minus 12. Now I'm going to write this a bit slow. So it's minus 12 divided by s, but also divided by s squared. So what does that mean? Well, it's 12 divided by s, and also s squared is 12 divided by s cubed. Okay, so now we have, in terms of the picture on the previous page, we've done the Laplace transform on both sides. We've translated the differential equation into an algebra equation. We put in the initial conditions, and then we solve the algebra equation. We've got the big B of s. And now we just have to do the last bit. We just have to send it back. We have to do the inverse Laplace transform. So we probably need to write something from the tables here. So you got these 1 over s squared, 1 over s cubed, and they're in the tables. 1 over s to the n gets sent to by the inverse Laplace transform t to the power of n minus 1 all divided by n minus 1 factorial. Okay, now it wouldn't be the worst thing in the world, but you shouldn't be going back to t here. Like if we draw a picture, let's draw a picture. We started here in the x domain. Then went to s domain. So differential equation, Laplace transform, algebra equation. Then we got b of s. And now we have to go back to b. It won't be of t because it's the x domain, b of x. So little big B of s is going to go back to b of x. So Laplace transform both sides. Little b, big B of s, excuse me, goes back to big B of x. I'm going to fix the 36. And what about 1 over s squared? We're going to use the orange formula. So 1 over s squared goes to t to the power of 2 minus 1 over 2 minus 1 factorial. Minus 12. And what does 1 over s cubed go back to? T to the power of 3 minus 1 over 3 minus 1 factorial. So the 2 minus 1 in the first term is just 1. T to the 1 is just t. So you get 36t, and 1 factorial is just 1. And then the other one, oh god, I'm a donkey, aren't I? Going on about the x then, and I do it. Dub. So sorry, x to the 2 minus 1. X to the 3 minus 1. 36 x. Yeah, now the 3 minus 1 factorial is 2 factorial, which is 2. So I got 12 over 2, which is 6. And then x to the power of 3 minus 1 is x squared. And we have a little plot of it there. Okay, so that's probably enough for this week.